Good morning, everybody. And by everybody, I mean the one person watching. Um, so today I am going to be doing some YT development. And if you have any questions or anything you want to chat about, go ahead and drop me a line in the Twitch chat. I am going to be following that as best I can while I do all the different tasks that need to be done for YT. So to start out with, I'm going to go ahead and change on over to my coding window. You can see, I think I've mentioned this before, but uh, my headphones actually turn off after about 5 minutes of inactivity, so I can't do, oh hey Clement, how's it going? I can't do this without music playing. So for instance, right now I'm listening to the Master Boot Record album Wares. And it's got Afterburner on. Alrighty, so let me go ahead and get myself up to date. Yeah, I'm in the Iwa refined map. I'm working on keeping notes for myself a lot more, in a much more detailed way. So let me keeping notes about which branch I'm on. Let me check out main. Ooh, yeah. Oh, do I not get to? I guess that's a mercurial thing. Okay. I'm going to keep my fork up to date real quick. Oh, wow, more viewers. All right, so let me bring this on up to date. If you have any questions or anything like that you want me to talk about or go over, I'm happy to do so. These are office hours, but I am going to start by digging into some pull requests and see where we're at with all that. So let me go ahead and take a shot here. I have a tendency to go top to bottom, so I hope you'll forgive me. This is sort of a last in, first out queue. Got a bunch of bug fixes that need to be addressed. Yeah, probably do need to refactor it to avoid fixing the same mistake 3 times. Oh, hey Josh, how's it going? Let's see, data label. Yeah, we've run into this before, but this looks good to me. I'm going to go ahead and merge this. Let's go back here. MPL version check. Yeah, I'd seen this one. So one thing I wanted to note about this, as long as I am chatting through stuff. Oh yeah, Dusty ISM is indeed possible. So Josh had sent me some data a little while back, and I haven't followed up with him, but I did take a look at it. And basically, the setup was pretty interesting. And in fact, Clement, if you're still watching, you might be interested in the basic outlines of this as well. So it's a HealPix pixelization of the sky for the, say, let's call it R and theta, and then, or I'm sorry, theta and phi, and then the R was in log-spaced bins, and I want to say there were 120 of them in log spacing. So it's not exactly the same as uh, R theta phi data with just a log bin, because they're not necessarily the way that and it was N1024 for the HealPix. Um, the way that HealPix works is it doesn't set up uh, what we would think of as logically rectangular um, grid cells. So they're close to logically rectangular, but they're not exactly logically rectangular. And so in principle, this can be loaded in using, it still can be loaded in using a hexahedral mesh, but the hexahedral mesh is going to have irregular spacing in R and theta. or in r, theta, and phi instead of just in r. So Clement's data, for instance, was in uh, log spacing in r, or maybe not log, but certainly stretched, but it was regular in theta and phi. So I was able to load it in. I don't think it was on my laptop, so I don't have that. My laptop is somewhere else, conveniently enough for me. And here, I'll actually load the data over here, or I'll load the window Josh tossed into the chat over here. So it's this data, based R, and you know what? Maybe that would be a fun thing for us to experiment with right now. So this is office hours. So let me give it a shot. So I think I stored it in, was it in data? It was like 10 gigabytes. So let me take a look. There we go. Yeah. So I'm going to go ahead and, oh, they are slightly different. Okay. Well, I will, let's take a look at this again. One thing I do need to do on this machine, let me, it's an unholy merge of those and another one, but same format. Okay, yeah, fair enough. Let me activate this. I got to get HealPy installed while I'm thinking of this. So let's pull up Jupyter Lab. Let me take a look at this. New Pi 3.9. Let's say initial load. Let me pull it in. So it is like -5 with wind chill here, but the thing is the wind is very low, so I'm not really sure why. So yeah, that sounds amazing. So I'm going to read this out loud in case folks see this on later on. Nobody will. But the point of this is to be able to visualize the data in 3D and VR, so we can design a literal laser hologram with a holographer in Sweden. I hope that I said holographer correctly. You know, the fun thing is I've been looking at, there's this laser engraving machine at the Fab Lab here that can do various different things, and I was going to bring in some data viz and have it cut it into MDF, but it turns out that it caught on fire last semester, and they haven't been able to replace it since then, so it's currently down. So I guess I'm going to have to wait on that. Now it's been a while since I've used HealPy, but oh, looks like it hasn't even been installed yet, so it's going to give me an error there. So let me go ahead and clear the output. We'll import HealPy in just a minute. So np.from file, I think it's from file when we've got an np file, right? It's been a while, so we'll just call this data. And now, if I remember correctly, it was shape 128. I think I wrote that in the README file. Yeah, there we go. So I'll reshape this. Probably need to specify the... No, do I need to specify the D type with an NPY file? Oh, I can... Oh, it's not from file at all. All right. And... it's been a while. I'm sorry about this, folks. I'm going to keep apologizing. Okay. We'll load this. We're not going to fix any imports. We'll just call this data. Yeah. Well, I haven't had a holographer since I moved to Illinois, so it's been a while for me. Watching me work is extremely instructive. Well, thank you. I think this is how I. So I have to say that one of the things that I learned from Greg Wilson was to. He told me once that it's important to make mistakes that people see when you are instructing, and so I have taken that as sort of a license to just make lots of mistakes. All right, now it's taken a while to load in. And my suspicion there, so I've got I'm working on what was once upon a time a pretty beefy system about, oh, hi Samwise. Um, oh, I'm glad to hear that. This system about 10 years ago, I guess 11 years ago now, was pretty beefy, but it's been a long decade. All right, so let's see. I forget if MPY gives us a shape. I don't. Oh, it does. All right. So let me check on HealPy. HealPy is now installed, so let's go ahead and restart this. I am not going to reload the data set. But we now have this HealPy system, and what I'm going to do is keep in mind that the way HealPix yes, failing to remember how SQL works. Yes, that. um, I do that constantly. I did that this morning. Forget how SQL works. So if we look at the shape here, typically this isn't what we would think of when we think of as a regularly structured array. But that's because, much like grid arrays, there are implicit structures that are embedded into it. And those implicit structures are related to the HealPix pixelization of the data set. So the HealPix pixelization of the data set, it's set to n equals 1024. HealPix has embedded into it the notion that there is an up direction, and that the nth value corresponds to a particular centroid direction and also a particular direction for the components of that value. So, or rather, the vertices. So, given an I, so any one of these values, inside I can point. Given an I here, because I know the pixelization level, that corresponds uniquely to a particular direction. So if we look at HealPy, and I've got HealPy here installed, and HealPy is a really nice, set of systems for, or a really nice wrapping of of the HealPix process. And HealPix is a pretty cool, system. If I'm remembering correctly, you could get away with doing most of it just including headers. And so it was, really fun to implement that. And a long time ago, I implemented my own wrapping of it, but it was really small compared to the functionality that is exposed in HealPy. And so I'm really grateful to be able to use that. If we do pix to ang, this takes two parameters. You can do third and fourth parameters, which I think are the offset, latitude, longitude, or maybe nesting. Yeah, I'm not going to do those just yet, but this gives us, if we have an n side of 1024, which according to my notes we do, we can specify that, say, pixel 1, it will give me the angles. And so it gives those angles back to me in theta and phi in radians. And I believe what we can in fact do is we can say HealPy. Oh yes. So I will pull this up and make sure that it goes into the into any notes that I post on this a little bit later. But yeah, Josh has just posted in the chat a link to the paper. So if I'm remembering correctly, there is a way to do this in a vectorized format where what we do is we just say, give me all of the angles and vectors. So let's give that a shot here. It is 1024, and let's see if we do this with just these three, and it does return it to us. So here at 1024, it gives us what looks like an array of where the first element, or a set of arrays where the first element of that tuple of arrays is the theta and the second element is the phi. Now, there might be a better way to do this, but we can simply do it by saying n side equals 1024, ipix is equal to np.arange data.shape 0, and then we can say theta phi is equal to heel pi pix to ang ipix, n side ipix. Now let's see how long this takes, because I think, yeah, it's pretty much instantaneous. So let's take a look at that. And I'm actually going to, because this is, kind of, oh yeah. Yeah, nest defaults to false. So let's go ahead and we'll say true here to turn on nesting. And then I'm curious, I can never remember how these things go, so I'm going to do a plot of theta because I want to see what we've got here. So this is how the theta varies. Now, the important thing really here is not that what it looks like, but really just that this is a total tessellation of the sky, and it does so in an order that might feel non-intuitive, but isn't. So, getting back to where we started, we've got logarithmic distance in distance modulus between mu equals 4 mag and mu equals 11.5 mag. So we'll have our, we're going to call this R, and I know that's going to, and we're going to say that R is in log space, let's see, in log space between those. So I think that means I can do this in linear space between those two values, right? So that would correspond to, am I doing that right? People say you don't. Oh, people say you don't use rhombic dodecahedra, but every time you compute a heel pix position, you're using a rhombic dodecahedra. Fair enough. Fair enough. Been doing a lot of dodecahedra work lately. I got some, yeah, anyway. Yeah, it's a good one though, Josh. All right, so we're going to do that. Nah. And we've got our theta and our phi. Now keep in mind, this is pix to angle. So if I'm remembering, that is actually, that's giving us our centroids. And what we really need is we need our edge values, which according to the heel pix documentation, which I'm looking in here, is actually convert angles to 3D position vector. No, that's not it. Vectors, no. Inside XYZ nest to ipix, no, that's not it. Ang to pix, no. Is it boundaries? Yes, XYZ for positions on the boundary of the pixel. Okay. So we are also going to be approximating here. So heel pi dot boundaries can get us our theta and our phi. So n side is, I think I defined n side as a variable up here. Yeah. Boundaries n side, the pixel identifier is just going to be our ipix. And then we will get x, y, z from this. Now, I know this is going to be a little gross because I'm going to have to convert these XYZ back into our theta and phi, but I think there's a way to do that. Too many values to unpack. Expected 3. Let's see. We'll call this bvex for boundary vectors. Right, we've got 4 corners, 3 components for each corner. Yeah, that works. So we've got all of our 4 corners here. So we will say now convert these back into So that's a good question. My assumption here is that it's scaled to the unit circle because it's giving us XYZ vectors, not r theta, or not theta phi. I would prefer theta phi, but I don't see how to do that. Oh, and I also need to specify nest equals true here. But my guess is that, yeah, here we should be able to bvex star 2 dot sum axis equals 1. I think this should give us 0 or close to it. Yeah, so that's giving us close to 0. So that means that the range, so P to P is peak to peak or peak to trough. I don't know. Anyway, but it's the range basically. So this is suggesting that they're all essentially unique. And my guess is that they are all essentially unique at 1. And let's take a look. Or not unique. They are all essentially identical. Yeah, they're all equal to 1. Okay, so let's go ahead and scale this. And now you get to see me always get confused with my thetas and my phis. So let's take a look here. Bvex. So theta is equal to bvex everything. Let's see. Yeah, I do too. I blame physicists as well. All right. So we can ignore our r, but our theta and is going to be a tan 2. Is it a tan 2 or is it arc tan 2 in NumPy? Oh, I shouldn't have reassigned that. Oh well. It's arctan 2. So, oh, hi Catherine. P.arctan 2. Oh no, now there's L and B. But I'm not sure what L and B are. Oh no. Bvex everything. And then oh, okay. Galactic longitude and galactic latitude. Oh boy. I have to say, every time that I talk to someone familiar with observing, I feel very silly. No, I'm trying to do the exact opposite. So HealPy boundaries gives it back to me in XYZ. almost there. I don't want that to be bvex 2. Where did I get that 2 from? Let's see. Theta is equal to np dot arctan2 of that. And so then here, that's the numerator. Here's the denominator. And here phi np arctan2 of y comma x. Bvex. Now this should roughly follow the exact same, here let me, so I'm going to plot both of these because I happened to plot theta and phi earlier. They should roughly follow the same thing. Any variance due to them being the corners instead of the centroids shouldn't be visible. So let's see what it looks like. Oh, and as long as you're here, Catherine, congrats on the Nature paper. All right. Yep. So theta looks right. Now let's go back to phi. Yeah. All right. So this has given us our basically exactly what we want. And here I got to note that like this is the further we get into this, the more uncertain I am that we are having that we are gaining something over binning it into strict XYZ. But let's keep going here. Because if there's one thing that I like doing, it's continuing on. So we've got our hexahedral mesh here. All we need to do now is augment it with our left and right edges for R. R here is, yep. So R has a shape of 120, and our phi has a shape of that by 4. So we're going to need to expand this array. So if we take phi and we think of it as having boundaries, we can turn them into hexahedra, which have 8 vertices, by doubling up the R positions. Now, I have a real easy time getting pretty confused about broadcast operations in this sense. So why don't we do this the slow way, which maybe it won't even be that slow. And we know that our final vertex is going to have a size, or our final set of coordinates there's a way more efficient way to do this if I can get adjacency information. Take a look. Yeah, I know I'm going down a bit of a rabbit hole, But here, I'm going to look at the first 5 of these in phi. Yeah, they're not exactly adjacent in the way that I would have hoped. Which makes sense because they're not really adjacent. So, all right, let's just do it. So what we want to feed in here is we want to feed in a proper set of hexahedral meshes. Now, keep in mind that that's not, strictly speaking, they're not hexahedra in the sense that they're not regular hexahedra. There is a slight curvature to the surface along all 6 faces. But for our purposes of approximation, we're going to ignore that. So to construct a single one, we know because of the shape of our phi and our theta, we know that this first one has corners here. So pixel I has these 4 corners projected at R and the next R value out. There are 120 slices that are evenly spaced. So I'm going to apply a fixed width to those. Or rather, maybe I'll just for now ignore the innermost slice. And we can construct our set of arrays in that manner. So we'll do this the slow way. For I in range data.shape 0. And again, I know this is the slow way. We will have our vertices equal to an array, or equal to a list, and we will append phi I 0, phi I 1, phi I 3. Oh, sorry. Each one of these is going to be a set of these values. So our first one is going to be I'm having a really hard time not just trying to unroll these loops. Please forgive me. I'm sure this is fascinating for everybody. The way that we can... Okay. All right, so we've got 8 for each one. So in principle, if we could stack them such that it goes phi, or r theta phi, r theta phi, r theta phi, r theta phi, and then the next r theta phi, r theta phi, r theta phi, for each of those, then we would have 8. It would be a set of the shape of our result would be 1, 2, 5, 8, 2, 9, 1, 2, comma 8, comma 3. So let's try to just do that, because then we can actually construct the vertices inside a NumPy array, feed them in much faster, and then we won't do any vertex deduplication, which we could do, but we're not going to. And instead, we will just have all of our fixed values. So if I'm thinking about this right, phi has this shape. So all of those, we want to stack first our R values, we'll do it in theta phi r. We'll try it with just two of these dimensions first. So theta and then phi. If we stack that, we end up with an array that should be 2 by that. Now, we can stack this along the last axis instead, which will add on there. But we actually want to stack it such that it's along the middle axis. So now we have these, and it's a size of 4. So this will be our theta phi set of values. And now what we want to do is we want to augment that with a set of r values. Our r values right now are of shape 120, right? So what we want to end up with is we want to end up with a set of theta phi so np dot stack theta phi. Actually, you know what? Let me just make an empty array. Empty array of size data dot size, not data dot shape. Comma 8, comma 3. So that will be our set of vertices. Yeah, of course. Oh, you're killing me. This would be so much easier if I just... So a long time ago, I worked on I worked on a front end that used advanced radar data. And what this did was, instead of trying to make everything fit into a regular r theta, what it did was almost exactly the same as as the data that but inverted. So what it did was radar sweeps around and it samples at a fixed set of distances. So it's kind of like sweeping around, and there are little things, but there's a little bit of wobble as it moves up and down, and this is the exact opposite of that data set. It's now also obvious to me that whatever I had done on my laptop a couple weeks ago was not the correct loading of this. Oh. Josh and Catherine, you stumped me for today. Anyway, let's see what we can do with this anyway. So if I were to just load this in as, let's say, particle data sets, I think that would be a little bit faster. It's not going to look as pretty, but we will take a shot at it, just so that I can at least have something show up here. We're going to say HealPy pix to vec here. And I'm actually going to create a new notebook, start over from scratch, and then I'm going to kill this kernel. I'll come back to this, but I want to have something to show for this today. Pretend it's particles. we'll get some XYZ vectors. Now our actual XYZ vectors, so we'll call this, our actual XYZ vectors will be these multiplied by our radius. So r is equal to np.mgrid 4 to 11.5 on 20J. Oh, it's still loading the data. There we go. Okay. All right, so r is equal to that. Remember that we can scale x, y, z based on that. So r is equal to the square root of x squared plus y squared plus z squared. So we should be able to all right, so x, we'll say yt data is equal to a dictionary, and here we'll put particle position x is equal to x times r, insert a new axis, yep, particle position y times r, insert a new axis, particle position z, and then we'll just call this, I don't know what the field should be called, so I'll just call it that. And we'll ravel all of these. Okay. What did I do? Oh. So yt.load particles data, and then let's do vbox is equal to I gotta add a new thing here too. Min max mix max to data particle position x dot min, and then we'll do the max as well. Do y. Whoa. get our extents here. I probably should load it in something slightly smaller because we're making an awful lot of new sets of values here. Ooh, and I'm about to turn into a pumpkin in about 10 minutes. I want to revisit this one. I'm going to leave a comment. Yeah, I guess I am asking it to be really big at this point. Let's see. Sometimes when I sit on these streams and make mistakes, I'm reminded of the Zach Galifianakis Between Two Ferns. Conan just says, Zach mumbles angrily. Oh yeah, that should be YT data. Okay. Now these are huge arrays at this point. The nice thing about HealPix, of course, is that all the position stuff is implicit, and we've just made all of that explicit. So hopefully we'll be able to still deal with it. Yeah, I think that's the right order. So it's going out there, it's building a bunch of unnecessary indices because we are, everything is in the same array, so it doesn't actually need to build these indices, and that's something that in the future would be nice to fix, or at least to make it work a little bit more reliable way. One thing I am going to do, as long as I'm doing all this, I'm going to save this. In an external file. Oops. Create dataset. Let's call this X. Actually, I could probably just do this a little bit simpler. For k in YT data, f.create dataset k data equals YT data k. That should do it. Could probably compress this for a fair bit of gain, but not going to do that. Yeah, it's still loading the particles. I'm tempted to cancel that because right now everything's resident in memory, whereas were I to split it up into files on disk, it would be able to do lazy loading. I'm going to interrupt the kernel at this point, see if I can get it out. Because from my perspective, saving it on disk is going to be a much more valuable way to do this, so that I can also provide it as a memory map instead of keeping everything resident. Yeah, I've really hosed my, I've really messed up my Jupyter Notebook here. I guess having these big, I guess what would they be? Each component's probably 10 gigabytes. So I've got a fair bit of memory in usage right now. Which I guess makes sense with how we're seeing this behave. Let's see, I last saved at 1024. Yep, that makes sense. So let me go ahead. I'm going to kill the kernel from the command line. Hi, Schwarzschild, HS. 1684350. In just a few minutes, I'm going to have to I turn into a pumpkin. There we go, shutting down. So I'm going to run this, but this time let's cancel out my loading of particles. Okay, restart and run all cells. We'll go ahead, we'll load it in. Let's get my HDF5 file on disk. Oh yeah, it's dead. Okay. Let's reload. And then I am going to turn into a pumpkin any second now, so I'm going to have to sign off in just a moment, but let me at least get my HDF5 file so that it's not a total fumbling around morning. And then I think I'm going to have to sign off. Got to fix that DECGL thing. All right. Yeah, reset. So those of you just joining, sorry I'm going to have to go soon. I might be getting really choppy too, what with all the memory that's in use, but basically we've been working on trying to load in some dust maps that are defined in a HealPix pixelization of the sky in radial bins. The way that I was doing this initially was trying to get R theta phi out, but we decided that that was too big for the size of data that we had. So I went ahead and I started taking a look at how we might be able to load it in, pretending that it's particles. Looks like things are clearing up on my end here. So I'm going to save what I've got. Oops, nope, can't do that. I'm going to save what I've got here by dumping the data out to disk in an HDF5 file that I can then load in later on using a more memory conservative approach. The way that I was doing it right now required everything to be resident in memory, which definitely not going to work. Oh, hey, no worries. This was super fun. I'm going to have to go, but I'm going to let this run, and then I will see if I can send this over in case anyone wants to give a shot with it. But thanks for joining me. I'm going to try to do this regularly, and have a good one, everybody. I hope you're all taking care of yourselves. Thanks.